So we sent Tim, your mentors here to introduce you, John Gong.
Mhm. Yes, my name is Dr. Jian Gong. I'm an astrobiologist based at the University of Wyoming. It is my pleasure today and over the summer working with Timothy Marijono as a mentor for the N3 program. I really appreciate this opportunity. Um, Timothy, thank you for your curiosity, drive, and your incredible work ethic. You always ask great questions during our meetings, and you took bold initiatives pushing the project forward. I wish you the best going to Purdue University studying computer science, and I welcome you back anytime working with me. Keep working on the project if you want. Um, okay.
Yeah, thanks, Dr. Gong. Can you all see my screen right now?
Yes.
All right, perfect. Then I'll get started right away. Hello, my name is Timothy Marijono, and this is my internship project this summer with help from Dr. Zhang Gong. First, some background. For a long time, humans have been wondering if there is life beyond our own planet. While we haven't met aliens within our own solar system, we have been discovering thousands of planets orbiting other stars since 1995. Exoplanets that could potentially be hosts to their own life. If this hypothetical life is anything like Earth's, it would have to be on a similar planet, small, rocky, terrestrial, and orbiting a star similar to the Sun. But where can we find these sort of planets? To try to find answers to that question, we began analyzing existing exoplanet data from the NASA Exoplanet Archive, primarily focusing on the common features of terrestrial exoplanets. But while the data we sourced is extensive, the scope is rather narrow with a comparatively low quantity of terrestrial exoplanets. That's what drove us to focus on potential correlations in the available data as well as to determine reasonable estimations. Thus, I programmed a set of statistical tools built specifically to analyze the NASA Exoplanet Archive's planetary systems dataset. These tools use machine learning to estimate some missing values and also includes an interactive graphical interface, numerous options to filter through the dataset and analyze certain features, and other functions not available in the tools available on the Exoplanet Archive. These tools include PCA and UMAP functions to summarize multi-column datasets, histogram and scatterplot functions with additional features compared to the ones on the archive, a table to compare the intersections of categorical factors, and a star map that creates 2D and 3D spatial visualizations of the exoplanets in the dataset relative to Earth. These tools are open source, so if you're interested in exoplanets or wish to improve on my code, I'll provide more information at the end of this presentation. By the way, here's a couple hypotheses we tested, plus some follow-up questions we come up with along the way. Starting off with, is a planet's orbital radius correlated to its type? This histogram, plus facets, compares each planet's orbit semi-major axis, basically the farthest they ever are from their host star. And as you probably noticed, most of them are condensed to the very first bin. Not a very easy to read graph, but that's where some additional things come in. This histogram uses the same data set, but instead compares percentage contributions to each bar. As this reveals, all the bars besides the first are completely filled with gas giants, which tells us that gas giants have significantly more variation in orbit radius compared to other types of exoplanets. But if you're worried about that first bar containing all the data, you'd be rightfully so. As it turns out, most of the exoplanets in the dataset occupy an area below 1 astronomical unit, which is our Earth's orbit semi-major axis. So follow-up question. Why are most exoplanets in the dataset closer than 1 AU to their star? This histogram uses a 0 to 2 AU range, but grouped by discovery method instead. While the blue section, representing the transit method, is mostly limited to below 1 AU, the red and yellow sections, radial velocity and microlensing respectively, are much more evenly distributed. Transits are when a planet eclipses its star and it causes it to appear dimmer. And planets close to a star tend to transit more frequently, which makes them easier to detect. That would explain why most exoplanets in the dataset are close to their star, They're some of the easiest to detect. So conclusions from this section. Gas giants have significantly more variation in orbit rays compared to other types of exoplanets, and the transit method used to detect most exoplanets tends to find planets much closer to the Sun than Earth is. For our other hypothesis, is the star's age correlate to the number of planets it has? This is a 2D scatter plot comparing a star's age to the number of planets it has. While it's not a strong relationship, I found that older stars have less discovered exoplanets on average compared to some younger ones, with very few stars over 9 Geiger years having more than 3 planets. Key being discovered. Older stars are likely dimmer, and thus when an exoplanet transits or could otherwise be discovered, it doesn't make as much of an impact. This gave us a couple follow-up questions. Let's start with Dr. Gong's follow-up question. Are exoplanets orbiting older stars harder to detect? For this, I decided to compare stellar age with transit duration, effectively how long of a window we have to detect an exoplanet when it transits. This graph, while mostly linear, contains a couple high outliers, which peak around the younger end at 4 Geiger years. This suggests the average transit duration does in fact decrease as the star ages. And as for my follow-up question, is there evidence that larger suns could engulf their own exoplanets as they grow? For this, I wanted to see if the average number of known exoplanets decreases as stellar radius increases. Since I already know the vast majority of known exoplanets were discovered by the transit method and are very close to their star, I also exclude other discovery methods to rule out planets at a relatively safe distance. This graph is heavily skewed to the right, past 2 times our sun's radius. There are few planetary systems with more than one detected exoplanet, suggesting that larger suns tend to have less planets that are close enough to them to be detected by the transit method. So conclusions, the stars over 12 Geiger years old have more than 3 exoplanets, unlike younger stars. Exoplanet transits tend to last longer on average for those orbiting younger stars, primarily past 5 Geiger years. And stars over 2 solar radiuses large tend to have less planets that are close enough to them to be detected by a transit. Now, for my takeaways. I signed up for this internship because I've been very interested in space, and over it, I've realized that much of it is due to the technology we use to explore it. Researching spacecraft like the James Webb Space Telescope, tests, and the discoveries they make has left me occupied for hours, and as we continue to innovate, I and other curious people will be there to learn all about it. Throughout this internship, I've also learned a lot about programming, flying with graphs, and managing my time, which should serve me well while I'm studying to get my computer science degree. To wrap this up, if you're interested in the data analysis tools I use, feel free to access the GitHub using this QR code or this link. Listed here are the datasets and catalogs I referenced for said tools if you want to check those out. Lastly, thank you to Dr. Gong for being my mentor this summer, to N3 for this opportunity, and to you, the audience, for your attention. To those of you watching this presentation live, I'd be happy to try to answer any questions you have. Thank you.
Wow, really excellent work.
Oh, we had a data science project too, besides machine learning projects and CAD projects. This is like so amazing that high school students are doing all these things that are at the cutting edge of what research scientists and PhD people are doing. I can't tell you how proud I am of all of you. This is amazing.
Yeah. Really great. Does anyone have any questions? And Tim, you could stop sharing, I think, at this point.
I'll just keep the QR code up.
And I hope all the parents are just as proud of
Yeah.
your students as well.